In this video we are going to talk about matrices and matrix algebra, and this is section 2.2 of the textbook. Right, suppose we have got two systems of equation. One has x plus y is equal to 6 and 3x plus 5y is equal to 22, and the other has v plus w is equal to 6 and 3v plus 5w is equal to 22. You will notice that what is different here are the names of the unknowns. So x, y, v, w in the second equation, and these systems are not different mathematically because the value that we are going to get for x will be the same as the value we get for v, and then the value for y will be the same as the value for w if we were to solve this system. And so the names that we give to these unknowns become irrelevant. What is relevant are the coefficients in the system and the values, the terms on the right side of the equation, right? And a particular way which is very convenient of capturing this essential information, these coefficients, is an array of numbers. So we've got 1, 1, 3, 5, and then 6, 22. Right, so for the first one, 1, 1, 3, 5, you notice that 1, 1 are the coefficients of the first equation. So the coefficients of the left hand side of the first equation, right? So here we had one coefficient 1 there, and then 3, 5, these are the coefficients of the second equation on its left hand side, right? And then if we look at 1, 3 in this array, you will notice that 1, 3, the first column, represents the coefficients of x, and 1, 5, the second column, represents the coefficients of the unknown y, right? And then 6, 22 are the terms on the right hand side of the equations, right? And this leads us to the concept of a matrix. So what is a matrix? A matrix is an ordered rectangular array of numbers. So for example, we've got a matrix A and the matrix B. And how do we measure the size of matrices? So we will talk about the number of rows and then the number of columns. So for example, if you look at A, it has 2 rows and then 2 columns. So we will call matrix A a 2 by 2 matrix, and we always start by the number of rows and then the number of columns. So for B, we have got 4 rows and then 3 columns, so therefore we will call B a 4 by 3 matrix, not a 3 by 4 matrix, because it has 4 rows and 3 columns. So a 4 by 3 matrix, right? And we adopt the notation A equals to Aij in these brackets, where Aij represents the entries of a matrix. So if we look at the subscripts I and j, I represents the row in which this entry is, and then the j represents the column. So we are able to identify every entry in a matrix by its row and column. So if you think of A that we had, you'll see that A11 is going to be equal to 1, because 1 is the entry on the first in the first row and in the first column, right? So that becomes A11, A12 is equal to minus 2, because minus 2 is the one on the in the first row and then in the second column, so that becomes A12. And then A21 will be equal to 3, because 2 rows, one the second row, the first column. And then A22 will be equal to 5, because that's the second row and then the second column. Right. In general, if we have an m by n matrix, we can write it as aij in those brackets, which translates to all these entries. So you notice that all the entries in the first row, if you look at the first subscript, it is 1 throughout, so 1 1 up until 1 there, because these are in the first row. And then if you look at the first column, you'll see that the second subscript is the one that is 1 1 1 and 1 there. And then if you look at the second row, again it's the same story. The first subscript is 2 2 2 2, and then if you look at the second column, you'll see that the second subscript is 2 2 2 2, and then up until the last row, because we have got m rows, so the last row will have m m m m, and the same for the last column will have n n n n, because we have got n columns. So that becomes the matrix. That's how we identify the entries in the matrix. So if m is equal to n, so this is a special case where the number of rows is equal to the number of columns, then we have got entries that we've got special entries that are along the main diagonal of the matrix, and these are A11, A22, A33 up to AMM or ANN, since n is equal to m in that case. Right, so those will be the entries for the main diagonal of A. Right, we can also think of, we've talked about algebraic vectors in chapter 1, and we can also think about vectors as a matrix with a single column. That is, if you think of the vectors that we had, so it will be written in vector form like that, and it can also be considered as an n by 1 matrix, so it will be n rows, so 1 2 3 up to n rows, and then just one column, so it becomes an n by 1 matrix. And this is convenient. You'll see as we go that this is convenient when we are doing matrix multiplication, right? And so let's look at how we can work with matrices. So we want to create have some rules to be able to add, to subtract, to do scalar multiplication of matrices, the things that we had in vectors, and see what are the differences and similarities between matrices and, for example, the set of numbers when we are doing addition, multiplication, subtraction, right? So the first thing is to think about how do we say matrix A is equal to B, and this is definition 2.2.3 in the textbook. Well, for the matrix to be, for two matrices to be equal, one thing that we need to look at first is, are they of the same size? So they have to be of the same size. And then the next thing is, every entry or all the corresponding entries should be equal. So if I think of A11, it should be equal to B11. A12 should be equal to B12, and so on. And this should happen for every row and every column, right? So in other words, every entry of A should be equal to the corresponding entry in B, right? Now we also want to think about the matrices, the special matrices that will play the same role as 0 and 1 in the set of real numbers. So we are talking of the uh, additive inverse and multiplicative inverse. So then we have definition 2.2.4, which says that a zero matrix O is a matrix with all entries equal to 0. And example 2.2.5, we have so in this case we have got 2 rows, 4 columns. So we have got a 2 by 4 zero matrix, and the other one is a 2 by 2 zero matrix, right? So we have to identify the size of the matrix because a zero matrix for a 2 by 4 will be different from a zero matrix of a 2 by 2, right? And now we think of the special matrix that plays the role of a multiplicative identity, and this is definition 2.2.6, and it says the n by n matrix with diagonal entries. So because now we have got an n by n, meaning that the number of rows is equal to the number of columns, we can talk of diagonal entries. And if all the diagonal entries are equal to 1 and all the other entries are zeros, then that n by n matrix is what is called the n by n identity matrix, and it is denoted by in, and the n identifies the number of rows and the number of columns, or we can just call it I if there is no confusion. So for example, we are dealing with 3 by 3 matrices. We might not need to say I3 because we are just dealing with 3 by 3 matrices. So that's when we can call it I, when there is no confusion of what we are trying to say, right? And there are some examples. So we've got a 2 by 2 matrix. We can see that the diagonal entries are 1, 1, 1 there, and then the rest are zeros. And then for a 3 by 3 matrix, we can see that the diagonal entries are 1s, and then the rest are zeros, right? How do we add matrices? Well, again, they have to be of the same size. So if you've got 2 matrices of the same size, then the sum of A plus the sum A plus B of these matrices will just be the matrix such that you add the corresponding values, the corresponding entries of the matrices. So if you take A11, if you want to find C11, you say A11 plus B11. If you want to find A34, for example, if you want to find C34, you're going to be saying A34 plus B34, and so on. So that's how you add. And then the definition for scalar multiplication of matrices. So if you have a matrix A, and then the product RA, where R is a real number, will just be if you look at the entries, so there's supposed to be AIJ here, not AJ. And So what it means is you just multiply every entry of A by R. That's how you get RA. You multiply every entry of A by R, right? So that is it. And then in particular, if you take the special case where you say minus A, then that means you're just going to multiply every entry by minus 1, right? And if you want to find the difference, then it becomes obvious that you're just adding A plus minus B, right? And your minus B would have found it using definition 2.2.10. Right, let's go on to matrix multiplication. So in this case, if you are going to if you want to for matrix multiplication to be defined, instead of the sizes being equal, if you're doing the product AB, then the number of columns of A has to be equal to the number of rows of B, right? So the number of rows and the number of columns of P might be different, but what needs to be the same is the number of rows of A and then the number of rows of the number of columns of A and the number of rows of B, right? So the matrix AB becomes an M by P. So it will take the number of rows of M and then the number of columns of P, right? And how do you do that? So then you'll have a formula like that, and what you need to just remember is if we look at, for example 2.2.13, to just illustrate this formula, is we take, so if we are doing A times B, if we want the first entry of this matrix, of the matrix that we get the product, we are going to say the first row times the first column. If we want, for example, if suppose we call it D, the product. So if we want to find D12, then we are going to take the first row of A and then the second column of B to be able to find D12, right? If you want to find D13, we are going to say we are going to multiply, do a dot product of the first row of A and then the third row of the third row of B, and that becomes D13. If you want to find D21, you're going to take the second row of A and multiply by the second row of B, right? So how do you do the dot product? Well, it is a dot product. You just, so suppose we want to find D11, what we are going to say is the first row, so we are going to say 2 times 1 plus 0 times 0 plus 1 times 1 plus minus 4 times 2. So we get 3 plus 1, that's 4. We get 2 plus 1, that's 3, minus 2 times 4, so minus 8. So we get 3 minus 8, which is minus 5. So that will be our first entry. And if we do the second entry, D12, as I mentioned, we will take the first row and then multiply with, we do a dot product with the second column, and you can try this and see that you get minus 24. So in other words, we can have all the the entries. You can do it as a simple exercise to verify that the entries are correct there. And for a plus 2c, so we want to do a plus 2c, then we multiply c, every entry of c by 2, and then we add it to a. That is simple enough. And if you want to do c minus a, then we start by finding minus a. So we multiply every entry of a by minus, and then we say c plus that minus a that we found, and then we find what we want. So you can verify if all these entries are correct. Right, that is all for this video. We'll continue with some properties on addition, multiplication of matrices. Right, thank you.